Welcome everyone. My name is Rafael Vareto. I am a PhD student here in Brazil. This work was conducted in partnership with PhD Dr. William Schwartz, my advisor. Both of us are affiliated to the Federal University of Minas Gerais. In this presentation, I will introduce you to the approach designed to perform an open set face identification using ensembles trained on clustered data. Face recognition can be described as determining the identity of a subject using the face. From a technological perspective, smart face recognition examines visual data where people usually observe faces. Essentially, automated systems consists of either closed set or open set tasks. The former, closed set, comprises the identification of only previously enrolled individuals, whereas the latter, open set, recognizes the identity of registered subjects and also filters out unregistered persons. So there is a great demand for open set technology, since the vast majority of real-world face recognition problems consists of a finite number of persons of interest in comparison to innumerable unknown individuals. In the past years, very few open set methods have been proposed. The listed papers on this slide comprise works from 2015, 2017, and 2019, which once attained state-of-the-art results. So the first, DeepID3, comprises a deep neural network that learns a rich pool of facial features. Gunter et al. Evaluates 3 similarity assessing algorithms. Vareto et al. Assume that vote list histograms behave differently for queries comprising gathered enrolled subjects and unknown individuals. And lastly, ShuffleFaceNet is a lightweight architecture that uses no more than 4.5 million parameters. The main contributions of the proposed work is a scalable open set approach that dismisses the need of retraining with the addition of new individuals. It is easy to implement and contains very few parameters. We also evaluate the approach on different data sets and protocols. And I mean LFW, labeled faces in the wild, and YTF, YouTube faces. The development of a baseline that can be considered in future works regarding open set face recognition. In this slide, there is also a chart, 2 charts, that illustrate the common behavior of the vote list histogram in our approach when a query sample has been enrolled in the gallery set, the chart in blue, or when it belongs to an unknown person, the chart in red. Additionally, there is an equation that explains how the algorithm thresholds and considers a face sample to belong or not to the gallery. As you can see, it gets the value of the top scorer bin and divides by the mean of the second and third best bins. The pipeline goes as follows. The approach employs the affinity propagation clustering algorithm on all samples available in the gallery set. Then a query sample is presented to the collection of clusters, and the clustering algorithm picks the most similar clusters. In this example, clusters B and C, and sets up a training subset SC with subjects 2, 5, 7, and 8. The training subjects from cluster SC are randomly partitioned into 3 positive and negative subsets before feeding an ensemble of partial least square models. In the picture, 3 random partitions are executed to feed the partial least square models, the PLS models. The probe sample is then presented to the ensemble in pursuance of response values R1, R2, and R3 And these response values are used to increment the histogram bands when they fall in the positive subset, the green side of the random partition. The histogram is sorted in descending order and becomes a ranking. And the previously described thresholding technique is employed to find out whether the probe sample belongs to the face gallery or not. Now, talking about the data set, we adopt the labeled faces in the wild, LFW. LFW was initially proposed for face verification. It contains more than 13,000 uncontrolled face samples of almost 6,000 public figures. And following many works from the literature, we adopt the funneled aligned LFW images. And since it was proposed for face verification, in 2017, Gunther et al. Proposed a new protocol in which they split LFW subjects into 3 disjoint groups. 602 identities containing more than 3 face samples compose the gallery set. Around 1,000 individuals constitute negative classes, and more than 4,000 identities with a single image each represent the unknown set. And 2 extra protocols and their respective evaluations are detailed in the manuscript. In the first table, Table 1, presents the cumulative match characteristic results, the CMC results, as we gradually increase the number of PLS components from 5 to 20. Since there is a minor advantage in using a particular dimension size, we set the number of PLS components to 10 for all following experiments. Table 2 exposes how the number of PLS models affects the implemented method. There is a meaningful improvement when varying the ensemble size from 30 to 100. However, we observe no significant accuracy increase when the number of regression models exceeds 50 learning algorithms. Therefore, we fixed the number of PLS models on 60 in the subsequent experiments. This chart presents the maximum achievable recognition rate, MAR, proposed in the paper described in the footnote. It indicates the upper bound rate for both filtering and identifying pipeline. Failing to select the best clusters results in trouble returning the correct identity for a given probe image, as the chart shows that an insufficient number of retrieved clusters severely diminishes the approach efficiency. So based on the experiment, we set the number of retrieved clusters to 20. These figures contain the comparison between literature methods in total accordance with Gunther protocols. The chart on the left presents the closed set CMC curve, in which the proposed method, indicated as COT, holds a superior performance up to rank 10. The chart on the right shows the open set ROC curve, showing that the proposed COT achieves higher performance on discarding unknown subjects and identifying individuals enrolled in the gallery set. Further experiments carried out on different datasets and protocols are thoroughly described in the manuscript, so check it out. Finally, the proposed algorithm combines a clustering method with an ensemble of regression models, so that it either retrieves individuals from the gallery set that present substantial similarity to the probe image, or considers them unknown subjects. Unfortunately, LFW does not provide enough number of individuals for a pertinent study regarding scalability towards large face galleries. That's our future research interest, massive galleries. In summary, open set face identification remains a difficult problem and more effort is necessary to make it fully effective. If you're interested in the proposed approach, you can access the Smart Sense Lab website through the quick response code on screen. And just in case you have any questions or are interested in more problems, in more computer vision problems, please email me at rafaelvarito@dcc.ufmg.br. A special thanks to Ember-P, FAPMIG, CNPq, and CAPS. Thanks for your time.